In this module, we see together some analysis applied to a complex dataset. It consists of several sheets and it has been already discussed in Module 1. Firstly, let's revise the problem and how the data have been collected. A set of patients underwent several visits and, at each visit, several tests have been performed. We do have information about each patient and each visit. These details, of course, have been anonymized. We do not discuss here the details of the anonymization step, but in general, keep in mind that this is an important step and you must always do before sending or showing your data. Finally, results for urine and blood tests have been saved in a test in files called urinetest.txt and bloodtest.txt. In particular, we focus on blood tests. Let's load the data in R using the read.table function and selecting either equal true option to read also the name of each column. Once data have been loaded, we can inspect the first rows using the add function, which displays the first 5 rows. As you can see, the first 2 columns identify the visit ID, an information we must use to relate each visit to some specific patient. Furthermore, it is enough to print these first few rows to notice that we have missing information. If a measurement was not taken, the not available NA string is reported. This is very common in clinical dataset, as not all patients are expected to have a complete analysis of all possible markers. For sake of simplicity, we avoid dealing with missing information and we simply eliminate them. This can be done using the na.omit function, which deletes all patients for which we do not have complete data. This solution is indeed suboptimal, as we are discarding many data, which may still be valuable, even if they are incomplete. In general, the process of handling missing data is not simple. It involves understanding why data are missing and then trying to estimate those values, or trying to carry on the analysis using only the incomplete dataset. Furthermore, we eliminate the first 2 columns, since we do not need the visit ID to perform statistical analysis. Once the data have been cleaned, we summarized all available columns using the summary function. Since we have 10 columns, we can split the summary by first printing the first 5 ones and then the remaining ones. This step is very important since at this stage experts must check if values are reasonable or if they may contain errors. In these few examples we see together, we will see how tricky it can be to perform statistical analysis on the real-life problems. Let's start from the simple prediction problem. We would like to predict the values of creatinine using eGFR. As we saw in previous models, a linear regression model is, in principle, suitable to solve this task. To fit the model, we use the lm function. Now, look at the R call reported in the slide. We specify that our response variable, which must be written before the tilde symbol, is creatinine, and we want to predict its values using an intercept, represented with a 1, and eGFR. After saving the results in an object called fit, let's print the summary of it. If we only look at the metrics shown in this slide, everything seems to be fine. The p-values are basically 0, meaning that we have a statistically significant effect of eGFR to explain creatinine. Moreover, the R-squared coefficient is 0.48, meaning that using a single variable, we are able to explain almost 50% of the variability observed in the data. It is not the highest of value, but in a real-life problem, it is an acceptable amount. However, is everything really fine? Let's closer inspect our results. Since we are considering a simple linear regression, we can and we must plot the data as well as the regression line. I recall you that in order to fit the regression line, we can use the AB line function, using the fit object as an input. Look now at the picture. Even though the diagnosis indexes are good, the regression line poorly fits the clouds of points. Why is this? Well, it is evident that the shape of the black clouds of points is not aligned. Hence, a linear relationship model between creatinine and eGFR is not suitable to explain the data. In such cases, we say that we are in presence of non-linearities. In this case, we can come out with a simple and elegant solution to this problem. Indeed, we can fit a regression model of the form reported in the slide. The response variable, creatinine, is the linear combination of some intercept and the inverse of eGFR. By doing so, creatinine does not linearly depend on eGFR, but the model is still linear in the parameters beta 0 and beta 1. Hence, it can still be fitted using a linear regression model through the LM function. Look at the R command to fit the model. You can see that the nonlinear terms are included using that specific syntax. That is, we first need to write a capital I and then include the nonlinear term in brackets. As before, let's look at the R summary. The p-values are still equal to 0, but the value of R squared is increased, being almost equal to 1. The main focus point of this exercise is to convince you that, whenever possible, one should plot the data and inspect if everything is fine. In particular, we can plot the data in two different ways. We say that we are fitting a linear model between creatinine and the inverse of eGFR. Hence, if we plot the data so that we have 1 over EFGR on the x-axis, we do see a linear cloud of points which is perfectly fitted by the regression line. And what if we would like to show also the non-linear relationship between creatinine and eGFR? In this case, we can plot the data just as we did before, setting eGFR on the x-axis. However, since the relationship is not linear, we can no longer fit the regression line using the usual AB-line command, but we need to fit a curve. This is done using the curve command as reported in the slide. As you can see, the regression curve is now perfectly fits the cloud of points, much better than our initial solution. Consider a different problem, that is the one of predicting the urea level using all other available information. As before, we can perform this task using our linear regression model. The only difference is that we are no longer using a single regression variable. In these cases, we talk about multiple linear regression rather than simple linear regression. The R command is the usual one, that is the LM function. However, to specify that we want to include all other columns of the dataset in the analysis, we can simply write a dot after the tilde symbol. R will automatically understand that we want to use everything we have at our disposal. The regression is statistically significant, with a global p-value which is almost zero and R-squared that is 0.7, which is a very good amount of explained variability. Moreover, in clinical studies, it is common that we do not simply want to predict future values of the response variable, but we are also interested in understanding what are the most relevant factors that contribute to such value. This problem is addressed by looking at the statistical significance of each variable, which is summarized using the p-value. In particular, let's focus on the s_ht variable. This is not statistically significant, having a p-value of 0.6. Hence, in principle, we may consider to discard it from the analysis. However, instead of deleting s_ht, let's try deleting s_hp. In order to fit the model without a single variable, we can use the dot symbol followed by a minus and the name of the variable we want to exclude in round brackets. By inspecting the summary of this new regression model, we note that the value of R² is basically unchanged, but this time the p-value associated to s_ht is below the 5% threshold. Hence, by removing one variable, s_hb, a different variable, s_ht, which was not previously statistically significant, now it is. What is the explanation? The reason is indeed very simple, and it is clear once we plot the two variables. The value of s_ht and s_hb are strongly connected. Indeed, the linear correlation coefficient between these two variables is 0.9. Consider that the maximum possible value of the correlation is 1, hence 0.9 is a very high value. The interpretation is that these two variables are almost carry on the same information. It will be even possible to obtain the value of one of them just looking at the value of the other one. In these cases, we say that the presence of a variable is masking the effect of the other one. And this is one of the reasons why statisticians prefer to work with simpler models, that is, using as less variable as possible. Is there a way to prevent and anticipate cases like the previous one? Yes, R gives us a simple and elegant visual solution. To get it, we first need to install and load the CorePlot library. Then we can compute the correlation between any pair of variables included in the model, using the core function over the whole set of data. Finally, we plot the results via the CorePlot function, included in the package we just loaded. I suggest you to specify also the method equal ellipse option to get a better plot. Indeed, using this option, we have clouds with elliptic shapes that represent highly correlated variables. Moreover, the correlation may be positive, blue values, or negative, red ones. But in either cases, it is better not to include both variables in the model. It is enough to include only one of them, the one you prefer.